Hello, everyone. Hello. People are slow to join today. What's up? We'll wait about 30 more seconds and then I'm going to start. Hola. Yo, yo, yo. All right. I think I'm going to start. Actually, I'm going to start after I respond to this message. Okay, so today we are going to talk about rolling without slipping. Okay. Actually, I should look for a ball. Plenty of them around here. Okay. So I have a circle. Okay. Now, if this circle is rolling while slipping, then it's spinning, but it's not moving. Or it's spinning, but it's not moving very much. Okay? If you are rolling without slipping, then if you do a rotation, say one full rotation, then the circle has to move forward by a certain amount. Okay? So let me show you how that works. Let's imagine that you have a surface. Okay? And you have a wheel that is on the surface. Okay? And here's a point A. Here's the center. Here's a point A. The radius of the circle is R. And so it's going to roll without slipping. Okay, so it rolls like this, rolls in the clockwise sense. And so maybe it ends up over here after rolling. So that the point A is now up here, for example. All right, and a new point is in contact with the ground. Okay, so the amount that the wheel rotated is called theta. And this arc length right here, the arc length is called S. and the amount that the wheel moved forward, we're going to call x. Okay? So the fundamental thing in rolling without slipping is that the distance that the wheel moves forward is equal to that arc length if it is rolling without slipping. Okay? So, for example, if this wheel is observed to do one full rotation, then it has to move forward by this total circumference of this wheel if it is rolling without slipping. Okay? So this is the fundamental equation for something that is rolling without slipping. Now, how can we calculate this arc length for a circle? Well, that's really easy to do. The arc length is equal to theta times r. Okay? That's really easy to understand why that's true, because what if you did the arc length all the way around the circle? Then theta would be 2 pi. Okay? And you would have that s equals 2 pi r, which is the circumference of the circle. Okay? So this equation is for rolling without slipping. Now, what if we take the derivative? Oh, and by the way, I wanted to say that this equation is relating angular displacement to linear displacement. Okay? Relates angular displacement to linear displacement. So now what we're going to do is we're going to take the derivative of both sides of this equation. Okay? So I take the derivative, I get dx dt equals d theta dt times r. Now, why didn't I take the derivative of r? Because the radius of the wheel is a constant. Okay? So what is dx dt? Dx dt is the linear velocity, v. D theta dt is the angular velocity, omega. So rolling without slipping results in a relationship between angular displacement and linear displacement. Taking the derivative of that results in an equation between angular speed and linear speed. And then we're going to take the derivative again. Okay, again, r is constant. And the derivative of velocity with respect to time is the linear acceleration. The derivative of angular velocity with respect to time is angular acceleration. So this equation is a third equation that expresses rolling without slipping. Okay? And the reason I boxed this in is because this is the one that we're actually going to use in today's lesson. Okay? One of the things we have to be careful about here, so I'm just going to put be aware of the sign. Okay? If we look at this, the wheel is moving in the positive direction. It's rolling to the right. But if we look at the direction in which the circle is rotating in the clockwise sense, which we called the negative sense. So technically, there should be a negative sign in there, but for this lesson, we're going to sort of just redefine what the positive and negative directions are as needed. Okay, so that's why I just put beware of the sign. Okay, so this is one of the equations that we will use when you are rolling without slipping. Okay. The other equations are the linear form of Newton's second law, which is net force equals ma. and the rotational form of Newton's second law. And we're assuming that this is a rigid body so that its shape isn't changing while it rotates. Net torque equals I times alpha. That's the angular form of Newton's second law. So these three equations are the equations that we're going to apply to scenarios today. So what we're going to do is two examples. The first example is a yo-yo. Okay? And the yo-yo has inertia, which is given by I. It has mass m, and it has, I'm going to say outer radius, big R. Okay? So let's look at what does this yo-yo look like from a side view. Okay? From a side view, here's the yo-yo, and here's the center of the yo-yo. When I say outer radius R, I mean that this distance right here is R. Okay? And then it has a string that is going up right here, like that. Okay? And that string exerts a tension force on the yo-yo. Then we also could think about looking at the yo-yo from a front view. And if we were to look at a yo-yo from the front, it has it's kind of like two wheels, all right? And then there's that inner wheel in the center that the string is actually wrapped around like that, okay? So if we were to imagine that, so if we had sort of like could x-ray through the yo-yo, you would see this inner circle, okay? And I'm going to call the radius of that inner circle B, all right? So the yo-yo has two forces acting on it. It has tension, which is sort of acting a distance B away from the center. And then there is, I'm going to make that go out this way. And then there is the weight force, mg, which acts through the center of mass, which is the very center of the yo-yo, okay? Can you guys hear me? There's a question in the chat about, am I the only one who can't hear him? Can you guys hear me? Okay. So. All right. So, anyways, there we go. So, now in this problem, I want to talk about the signs, okay? So we are going to call the positive direction, the direction the thing will move. Okay? So if we have this yo-yo, it's obviously going to unwind downward, okay? So I'm going to call the positive direction of to be downward, okay? And then I'm going to call the positive sense of rotation to be the sense that this thing is going to rotate when moving in that direction. So I can see that if this yo-yo unwinds in the clockwise sense, it's going to move downward. okay? So I'm going to call clockwise rotations the positive sense, okay? And so the whole reason that we're doing this is so that this equation will hold true with positive signs, okay? So we're going to call the positive direction the direction that the thing will move in, and the positive sense of rotation the sense of rotation that the thing will do when going in the positive direction, okay? So this yo-yo is going to move downward, and as it goes downward, it's going to unwind in the clockwise direction. So those are both going to define my positive sense. Okay? So let's go ahead and do Newton's second law in the linear sense. Net force equals ma. All right? So if I look at what is the net force? Well, this yo-yo has two forces acting on it. It has mg going downward and it has tension going up. All right? And I'm taking downward to be positive. So my net force is going to be mg minus tension, because downward is positive. Mg minus tension equals ma. All right? Then I can do Newton's second law for rotations, which is net torque equals I times alpha. All right? If we think about this, gravity is acting through the center of the yo-yo. So gravity is going to have to cause no torque. And the reason that it's going to cause no torque is because it's acting from a location where r equals 0. And if you recall, the definition of torque is F perp times r. So if a force is acting from 0 distance from the pivot point, then it has no torque. Okay? So gravity has no torque. Tension, on the other hand, is a force that is offset from the center by a distance b. That distance is b. Okay? And furthermore, the rope is perpendicular. Okay? So the tension is going to exert a torque. T times b is the torque. All right? It's already perpendicular, so we don't need to do trigonometry to get F perp there. And it's offset from the center by a distance b. Now, why isn't it negative t times b? Well, because I can see that pulling up on the yo-yo from this location will cause the yo-yo to rotate in the clockwise sense. So that is a positive torque in this problem. Okay? So my net torque is going to be TB, because the torque due to the other force was 0, and that equals I alpha. And then lastly, I have the wheel is, or the yo-yo is not slipping. Okay, so that means that A equals alpha times B. All right, notice how I did alpha times B. All right, so we have to be careful here. And A equals alpha R. There's two radii. There's an inner radius and there is an outer radius. Okay, and the reason I'm using the inner radius is because that is the radius that the yo-yo is actually unwinding about. The string is actually wrapped around this inner radius, okay? So for that reason, it is going to be not alpha times r, but alpha times b, because that's what it's unwinding about, okay? So you will notice that that there are 3 equations here, and there are actually 3 unknowns. The 3 unknowns are tension, acceleration, linear acceleration, and angular acceleration. The other quantities and the other variables we see are mass, which was given, gravity, which is known, inertia, which is given, and B, which is given. So everything else is a given. Okay, so we have 3 equations for 3 unknowns. We need to solve that equation. All right. So first thing I'm going to do is I'm going to divide this equation by B. So I get A over B is alpha. And then I'm going to plug that in for alpha right here. So I'm going to get tension times B equals I times A over B. Okay? And then I'm going to divide both sides by B, and I get tension equals I over B squared times A. All right? And then I'm going to take that, and I'm going to plug it in right here for the tension. So I have mg minus, and instead of tension, I'm going to write I times A over B squared. I'm trying to solve for the linear acceleration of the yo-yo, all right? I'm trying to solve for the linear, I don't even think I said what I was going to solve for, but that's what I want to solve for, is the linear acceleration of the yo-yo as it falls down the string. So now I'm going to take this, and I'll take this equation and bring it down here. So now what I'm going to do is I'm going to add this term over to the other side. mg equals I over B squared times A plus MA. I'm going to divide both sides by M. So I have G equals I over MB squared plus times A plus A. Then I'm going to factor out linear acceleration on the right-hand side. All right. And then I'm going to divide by this big chunk here to solve for the linear acceleration. And what you get is that the linear acceleration is equal to g over the quantity 1 plus I over mb squared. Now I don't want you to, do not try to just write this equation down and memorize it, because the problems that I'm going to give you on the homework are not quite like this. Okay, there's little things that are different. The method of solving is what you really need to focus on. Okay. One of the things I like about this equation is we can see that the acceleration is gravity, okay, divided by a number that is clearly greater than 1, because it's 1 plus something, okay? So what that means is that the linear acceleration of the yo-yo is less than the acceleration due to gravity, okay? And if you've ever played with a yo-yo before, you know that if you just let it unwind, it accelerates down, but it doesn't accelerate as quickly as something you just dropped, okay? One other thing I wanted to say is if you're a little bit confused about the gravitational force exerting no torque, I invite you to imagine simply dropping the yo-yo without the string. What if you just didn't hold on to the string and you just dropped the yo-yo? Is the yo-yo going to spontaneously start spinning if you dropped it without holding onto the string? No, it's just going to fall maintaining its orientation. So what that tells me is that it's the string that makes the yo-yo go around and around. Okay, it is not gravity, it's the string. Because when we remove the string, it doesn't rotate. Okay? Okay, so for the next problem, I want to consider a wheel. The wheel has inertia I, mass m, and radius r. Rolls down a hill. Rolls without slipping down a hill. Okay, so the picture kind of looks like this. So we have a hill. The hill makes an angle theta with the horizontal. And then we have this wheel that is rolling down the hill. And what we want to do is we want to figure out what is the, well, we'll figure out a couple things. But first, let's figure out what is the linear acceleration. Okay. So if we think about the forces on this wheel, we have a friction force that is pushing back on the wheel. Okay, so script F. We have a normal force, which is pointing perpendicular to the incline. And we have a weight force that is going down. Okay, and from previous lessons on inclined planes, we know that because of the geometry of the situation, that is going to be the angle theta. Okay. So let's go ahead and define our directions here. So because of the way this hill is, we know that the acceleration is going to be that way. So I'm going to call that the positive direction. All right. And I'll call it the x direction in particular. Okay. And we can see that if the wheel moves in that direction, it is going to rotate this way. All right. So I'm going to call that the positive sense of rotation. So again, I'm calling the positive sense of rotation to be clockwise because of the way that we're viewing this. Okay. So I'm going to take my diagonal force here, which is weight, and I'm going to break it up into components. So I have normal force, friction. This is going to be opposite the angle, so it's going to be mg sine of theta. This is adjacent to the angle, so it's mg cosine of theta. All right, and keep in mind that the x direction is in that sense. Okay. So writing my linear Newton's second law, I'm really only going to use the x direction because that's the direction that this thing is moving in. It's not, the wheel isn't jumping off the incline. Okay. So the x direction, the positive force is mg sine theta. And the negative force is friction. Okay. Now what I want to point out is that when something is rolling without slipping, kinetic friction would mean the surfaces are rubbing across each other. Rolling means that the surfaces are not rubbing across each other. So rolling is actually static friction. Okay? Static friction. So this is static friction. Okay, this is static friction. This is static friction. Now, static friction is a little bit tricky because we have a formula for the maximum value of static friction, which is coefficient of static friction times normal. But this is not maximum static friction. You get what I'm saying? So this equation doesn't apply here because it's not maximum static friction. So we just leave friction as a variable. Okay. Now we need to apply the rotational form of Newton's second law. All right. And to understand that, I'm going to draw the wheel to be a little bit bigger over here. All right. And if we think about the forces on the wheel, we've got the normal force, which acts towards the center of the wheel, perpendicular to this surface here. Okay. We've got the weight force that acts straight down through the center. Oops. And then we've got the static friction force acting there. Okay? Now, just like before, the weight force is going to have no torque because R equals 0. So the weight force is acting through the center, so it has R equals 0. The normal force also gives no torque. Okay? The reason that the normal force gives no torque is you might recall that the formula for torque is F perp times R. All right? So the R value is not 0. It's the torque is acting a distance R away from the center. However, what defines perpendicular is it has to be perpendicular to the line connecting the pivot, which is the center, to where the force is applied. And I can see that the normal force is actually parallel to that line. Okay? So the perpendicular component of the normal force is 0. And so both the normal force and the weight force exert no torque, but for different reasons. Okay? Static friction is acting perpendicular to this line, and it's acting a distance R away from the center. So static friction exerts a torque of F sub S times R. And furthermore, it's a positive torque because we can see that this torque causes the wheel to rotate in the clockwise sense, which is positive for this problem. So rewriting Newton's second law for rotation, we only have one torque. So the net torque is F sub S times R. That equals I alpha. Okay. And then lastly, we have the equation for rolling without slipping. So we have 3 unknowns, once again, and 3 equations: linear acceleration, angular acceleration, and static friction. Okay? This equation is actually identical to, it's identical to this equation with 2 changes. Okay? The first change is that I don't have gravity. I don't have mg. Look at, I have mg sine theta. Okay? And furthermore, instead of tension, I have friction. But everything else is the same. So I'll just go through the steps really fast. So I get A over R equals alpha. which I then plug into the second equation, F sub S times R equals IA over R. Okay, which I then plug into the first equation, which says that the linear acceleration is g sine theta over 1 plus I over m r squared. Okay? Now, let's suppose I wanted to calculate static friction. I would then plug this result for the linear acceleration back into that equation. So static friction is IA over r squared. And I get, so I get g sine theta times I over r squared plus I over m. There. Okay. So notice how this is not the same formula as mu normal. And so that's the reason why you cannot use the equation mu normal. It's because it's not maximum static friction. It's below the maximum static friction. Okay, so that's my lesson for today, and I will see you in the Zoom room.